Before we dive into formulas and real-life effects, let's understand something very basic. When we dissolve something in a solvent, the number of particles it produces can change, and this changes the solution's properties. This change is captured by a very clever concept known as the Van't Hoff factor, denoted by I. Van't Hoff factor is a colligative property. Colligative properties like elevation of boiling point, depression of freezing point, relative lowering of vapor pressure, and osmotic pressure depend on the quantity of solute particles in a solution. But sometimes, solutes dissociate into more particles or associate into fewer particles than expected. That's where the Van't Hoff factor, I, comes in. Let's dive deep into the Van't Hoff factor, exploring how it changes the number of particles in a solution and influences key properties like boiling point, freezing point, and osmotic pressure. Here is my friend who is going to explain the concepts in detail.
So first of all, when we are talking about the Van't Hoff factor, that means Van't Hoff factor, it is a colligative property. Colligative properties is the property which depends upon the number of solute particles in the solution and not on the rate of solute. Second thing, the Van't Hoff factor, the abnormal molar masses. As I've explained that in 1880, Van't Hoff introduced a factor I, known as the Van't Hoff factor, to account for the extent of dissociation or association. So we have three formulas for the Van't Hoff factor. One is the normal molar mass upon the abnormal molar mass. Second is observed colligative property divided by calculated colligative property. And the third is the total number of moles of particles after association or dissociation divided by number of moles of particle before association or dissociation. In this case, the observed colligative property is the experimental value and the calculated is what we have done through the calculation. So there are three formulas that we would be using to calculate the Van't Hoff factor, that is normal molar mass upon abnormal molar mass. I repeat, observed colligative property divided by calculated colligative property, and the total number of moles of particles after association or dissociation divided by the number of moles of particles before association and dissociation. We are going to use this formula a lot because this formula will help us to get the value of the Van't Hoff factor. Why? Because with the equations and with the questions given, we can only know about it that after association and dissociation, what happens to the moles, whether it increases or decreases. As such, we cannot calculate the experimental values. So we are going to use this formula to solve the questions related to Van't Hoff.
As my friend has introduced these three formulas to calculate Van't Hoff factor, so before proceeding further, let us understand the terms, namely what is normal molar mass, abnormal molar mass, what is meant by observed colligative property, and what is calculated colligative property. Normal molar mass. This is the theoretical molar mass calculated from the chemical formula of a substance, assuming no dissociation or association. It is what you expect the molar mass to be under ideal conditions. For example, glucose has a molar mass of 180 gram per mole, and sodium chloride has a molar mass of 58.5 gram per mole. Abnormal molar mass is the experimental molar mass calculated using colligative properties, like depression in freezing point, elevation in boiling point, etc., which sometimes turns out to be different from the normal molar mass. This abnormality arises due to dissociation, breaking into more particles. Molar mass appears lower. Association, forming fewer particles. Molar mass appears higher. Let us understand the difference between normal molar mass and abnormal molar mass with help of examples. Let's take example of association of benzoic acid in benzene. Benzoic acid forms dimer due to intermolecular hydrogen bonding. Butene 2 molecules of benzoic acid. The normal molar mass of benzoic acid as calculated used its formula C6H5COOH is 122 gram per mole. But after the formation of dimer, because the number of particles decreases, the calculated molar mass appears higher than expected. Observed abnormal molar mass is around 244 gram per mole. That's nearly double the normal value. Let's understand by taking an example of dissociation of sodium chloride in water. The normal molar mass of sodium chloride, as per its formula, is 58.5 gram per mole. But when it gets dissociated in water, it forms sodium and chloride ions. So the number of particles increases. Thus, its molar mass now becomes far less than 58.5 grams per mole. It comes 29.5 gram per mole, nearly half. Observed colligative property. It refers to the actual measured value of a colligative properties as found through lab experiments. In simple terms, it shows how the solution actually behaves when a solute is dissolved, considering any dissociation, breaking into ions, or association, combining of molecules. Calculated colligative property. It is the theoretical value of a colligative property that you predict using a formula, assuming the solute behaves ideally, which means assuming no dissociation or association. A mole is a unit used in chemistry to count very large numbers of particles like atoms, molecules, or ions. 1 mole is equal to 6.022 into 10 raised to the power 23 particles. This is called Avogadro's number. Now I have explained you the terms we are going to use. Over to my friend for detailed explanation about what is association and dissociation of particles and other concepts.
Now the difference between the association and the dissociation. First of all, we need to understand what is an association, when that means when two small molecules combine to form a bigger one, and the dissociation means when the particles gets converted, or a big particle gets converted into smaller particles. So in the case of the association, the measured molar mass exceeds the expected value, because in that case the molar mass increases, and in the dissociation the measured molar mass value is always smaller because the molar mass decreases. I'm just telling you the differences. After that I'll explain you with help of examples. In the case of association, the Van't Hoff factor is less than 1. How? That I'm going to explain you. And in the dissociation, the value of the Van't Hoff factor is greater than 1. That again I'm going to explain you. So the colligative property values are lower than what we are going to predict it. That means it will be a reducing freezing as well as the boiling temperatures. Now in the case of dissociation, greater colligative values are seen. That means the greater boiling temperature as well as the osmotic pressure, for example. So this is what you are going to understand. This third property I'm going to explain you later when I'm going to combine, or when we are going to do the numericals which relates Van't Hoff factor with the elevation in the boiling point or depression in freezing point or the osmotic pressure. Today we are going to do just how to find the Van't Hoff factor, or the maximum, what is the degree of association or the dissociation. Remember that one more point we can write, that in association the number of moles after association increases. So that is why the Van't Hoff factor is less than 1, and in the dissociation the number of moles after dissociation, so therefore the Van't Hoff factor is greater than 1. I'll explain you with the help of example. And remember the trick, the number of particles of solute formed after association or dissociation is directly proportional to the Van't Hoff factor. Okay, so basically if the number of solute particles increases, then the Van't Hoff factor also increases. Then in that case the Van't Hoff factor will be more than 1. And if the number of solute particles decreases, then the Van't Hoff factor will be less than 1. Now why we are comparing it with 1? For non-electrolytes which neither dissociate nor associate, we take Van't Hoff factor as 1. So we are going to compare it with 1. That means when the number of moles before and after the association or dissociation remains same. So in that case, your Van't Hoff factor is 1. So as I was talking about the non-electrolytes, for example, glucose in water. So if we consider before adding glucose to water, it is just a one molecule, we can consider that the number of moles will be equals to 1. Now after adding glucose to water, it is still same. Now also the number of moles of solute is 1. So the Van't Hoff factor is total number of moles of particle after dissociation, that is 1. Number of moles of particles before the dissociation is 1. So the Van't Hoff factor will be 1. This we are taking it as a benchmark. Now, when the number of particle increases, the Van't Hoff factor is greater than 1. Now, when the solute particle decreases, the Van't Hoff factor is less than 1. Let us understand this with help of example. Van't Hoff factor is total number of moles of particle after association or dissociation divided by number of moles of particle before association or dissociation. Here it does not dissociate, that is, this is glucose in the water. So here the Van't Hoff factor is 1. Now in the second case is sodium chloride. So the sodium chloride in water, it dissociates into N plus ions and the chloride ions. Here the number of mole is 1, where here it is 1 and 1. So that means before the number of moles is 1 and after dissociation it is 2. So in this case, the Van't Hoff factor is total number of particles after dissociation is 2 and the total number of particles before is 1. So in this case, the Van't Hoff factor is 2, which is greater than 1. In the third case, it's calcium chloride, aqueous. So it is Ca plus 2 and plus 2 chloride ions. Before dissociation, the number of molecules were 1. Here, this is 1 and there are 2. So before, the number of moles were 1 and after dissociation, the number of moles were 3. So the Van't Hoff factor is number of moles of particles after dissociation, that is 3, divided by number of moles of particles before dissociation is 1. So the Van't Hoff factor will be 1 and it will be greater than 1 because more particles means higher Van't Hoff factor. You can see here that here when there were 3 particles, the Van't Hoff factor is 3. But in this case, when the number of particles got dissociated into 2, the Van't Hoff factor is 2. Now in the case of the acetic acid, which forms the dimer. So if I write the equation, there are 2 molecules of CH3COH which after forms a dimer, which is just the one molecule. So in this case, before association, the number of moles are 2 and then we are talking about the after association, it is 1. So the Van't Hoff factor is total number of moles after association, which is 1, and before they are 2. So the Van't Hoff factor is equals to half here, which is less than 1. So you can see here that the Van't Hoff factor is directly proportional to the number of particles. Here less number of particles, so lesser is the Van't Hoff factor. So basically you can say that when acetic acid is dissolved in benzene, then due to intermolecular hydrogen bonding, a dimer is formed due to association of molecule. For example, if I take one molecule of acetic acid, CH3, that is CO, and this is OH, and then you have another molecule that is CH3, and this is C, and this is double bond O, and this is O and H. So there has to be attraction between the atoms of two molecules. Like for example, this is your first acetic acid, this is your second acetic acid. So in between, there is an attraction between oxygen and hydrogen. So this will form a hydrogen bond. The hydrogen bonding is between hydrogen and either fluorine or oxygen or nitrogen, what we call it as FON. So here the hydrogen bond will be formed between the hydrogen and the oxygen. So this is the hydrogen bond formed. Due to this, they are going to come closer and form a double molecule, you can say a dimer. So basically there are two parameters that we need to consider, that whenever there is an association, the Van't Hoff factor is less than 1. So when we are talking about the elevation of the boiling point, that will become half of its value, and the depression in the freezing point also become half of its value, but the molar mass will become twice. So the molecular mass is always increased because there are two small molecules which are combining to form a bigger, so the molecular mass will increase. Now whenever there is a dissociation, what is happening here, that the bigger one is getting converted into these two smaller one. So in this case, the elevation in the boiling point will be the twice the normal value, the depression in the freezing point will be twice the normal value, and the molar mass will become half. Why the elevation in the boiling point and the depression in the boiling point, they are getting half? This is because we have done that the Van't Hoff factor is directly proportional to the number of solute particles. So when we are talking about the association, in this case, the number of particles decreases. So the Van't Hoff factor will also decrease. Elevation in the boiling point, the depression in the freezing point, and the osmotic pressure all are colligative properties. So they depend upon the number of particles formed in the solution. So in the association, as the Van't Hoff factor decreases, so the elevation in the boiling point and the depression in the freezing point as well as the osmotic pressure will. But in the case of dissociation, in this case the number of particles so the Van't Hoff factor will increase. So in this case, the elevation in the boiling point or the depression osmotic pressure, because we are putting the value of I, that is a Van't Hoff factor here. So it is in direct relation. So the moment the Van't Hoff factor value increases, the elevation in boiling point and the depression in freezing point or the osmotic pressure values will increase. In the association, it will decrease. Here I have taken the assumption that before the number of particles were 1 and after dissociation it became twice. Is that clear? So that is why I am using the word half and I'm using the word twice. But generally you can consider that in the association number of particle decreases, the Van't Hoff factor will decrease. So the colligative properties will decrease. And in dissociation, the number of particle increases. So the Van't Hoff factor increases. So the colligative properties will increase.
Now that you understand the concepts of association, dissociation, and the Van't Hoff factor, and how they relate to the number of particles in a solution, you might be curious about why ice cream melts faster, or why water boils at a higher temperature when salt is added. Or perhaps you're wondering how nurses determine the exact concentration of an injection. Well, all of this ties back to colligative properties, and we'll dive deeper into these fascinating topics in our next video. Stay tuned. If you found this video helpful, don't forget to like, share, and subscribe for more videos like this. Thank you.